Hello, everyone. Let's wait two more minutes until everyone comes in, and then we'll get started. All right. So it's 7:30, and so welcome everyone to our first astronomy class. I'm your teacher. My name is Clark Zhang, and I just finished graduating high school. I went to Montgomery Blair High School, part of their magnet program, and I'm currently heading off to Vanderbilt University, and I'm going to be studying mechanical engineering. My background in terms of astronomy is that I've been part of Montgomery Blair High School's Science Olympiad team for 3 years, and I've always done the astronomy subject as one of my subjects. And in the past 2 years, I've gotten second in Maryland states. So I think it's a decent accomplishment. Beyond my extracurricular activities, I've always been really interested in astronomy and stars and everything that happens in the universe. So I'm actually really excited to be able to teach you guys this class. So the structure of the astronomy class is pretty straightforward. We have 6 classes, an hour each, and in each of these lessons, I'm just going to be sharing some pretty cool things, I think, about astronomy. Astronomy is one of those subjects where you can only observe, you can only look at whatever is out there in the sky, right? You point a telescope up there, and everyone sees the same image. Everyone around the world sees the same image of a star, and everyone has a different interpretation of it. So I encourage you guys to, as I continue to share this content with you, I encourage you to raise any questions, raise any comments, put them out in chat, or unmute yourself and just say your thoughts, because I think that that's really what astronomy is truly all about. Does anyone have any questions on anything before we start? All right. All right, Serena?
Do we have to open our video?
Sorry, say that again?
Do we have to open our videos?
Oh, no, you don't have to if you don't want to. All right.
Okay.
Anyone else? All right. So let's get started. So today our first class is going to be about stars, how stars are formed, how their structures are, and how we classify them. Okay, so first question for everyone. What is a star? When I say the word star, what do you think of?
The sun.
Someone said, all right. The sun. Okay, something that emits light. Okay, anyone else? Anything at all? What about like a ball of gas? Or something really bright, right? Someone said a star shape,
Something you
yeah,
can see.
like that, right? Those are definitely stars. Anyone else? Yes, Rena?
Something that we can see.
Say one more time.
Something that we can see.
Something we can see.
We don't see your screen.
Oh, did I unshare? My bad. All right, there we go. Okay, so these are pretty good answers. So our sun is definitely a star. Stars definitely do emit light. They're really bright. These are also definitely stars right here. And stars are definitely something we can see, right? We look out into the night sky, we see lots of stars. So we have a lot of different definitions, right? So how do we come up with one definition for what a star is? Because that's what scientists like to do. We like to categorize things and put them into certain classifications. So the real definition, the scientific definition for what a star is that it's any object that's massive enough to start fusing elements in its core. So let's break that down. That's a pretty complicated sentence. All right, let's start from the beginning. So any object that is massive enough, right? So our first thing is that stars must be pretty big, right? To use the word massive to describe them, right? You and I, we're pretty small. Something massive is like the sun, right? Or some other stars out there, or like maybe like a planet, right? Let's say Jupiter. Jupiter's made of gas and stuff. That's pretty massive, right? So at least we know it needs to be something that's pretty big. That's the first part of the sentence. The second part is that it needs to start fusing elements. So it needs to fuse elements, and we're going to break down exactly what that means. This is a crucial part about what a star is. And the last part of the sentence is its core. So what do we learn about stars? We learn that stars have to be really massive. One, they have to be really massive. Two, they have to be able to fuse elements, and we'll explain what that means. And three, that needs to happen in its core. So know that a star has a core, just like our Earth has like a core of molten iron right in the center of our planet. So there's our sun. Our sun has a core. Yes, Rena?
Does the core of a star have to be hot or can it be cool?
Yeah, that's a good question. And we're actually going to explore that, but to give you a sneak peek, the core of the sun is going to be very, very, very hot. And that's why it's able to fuse elements. So let's dive into that. So, the science behind a star, fusion. Everything inside a star is powered by this word, this process called fusion. And I'll explain what that is. Fusion starts when you have two hydrogen atoms. We'll start here, two hydrogen atoms that are slammed together. So let's draw them. Hydrogen atom, hydrogen atom. So hydrogen is the very first element. It's the most simple element possible. All it is just basically a proton. That's it. One of the smallest particles in the universe. That's a hydrogen atom. And it's just like that, just like a ball. And let's label it hydrogen. So if you have these two hydrogen atoms, and then you were to slam them together really, really quickly, really force them together like that. And it has to happen with a lot of pressure, right? That's a lot of power to take two atoms and slam them together. It creates an explosion and lots of energy, a giant bang, right? And afterwards, after you slam them together, since you had these two particles, now it becomes a double particle like this, a particle with two little balls on it, basically. This is the core of the fusion process. So as you see, two hydrogen atoms are slammed together. It releases a lot of energy, and those two hydrogen atoms combine to form helium. If you take a look at the image here, even though it looks really complicated, it still depicts the same process. Right? We start with a hydrogen atom, another hydrogen atom, and they slam together, boom, with a lot of energy. That's what this bang is. It releases some other stuff, whatever. We don't really care about this. But what we do care about is that now we have this double, right? This double particle. And that makes sense. Take two balls, put them together, have two, and now you have a particle with two balls on it. Take another hydrogen atom, slam those two together, boom, another explosion. And now you get helium. You take those two helium atoms, slam them together, boom, another explosion, and you get helium-4. So this whole process, well, like there's a lot of particles happening, going on, but as you can see, there are a lot of explosions everywhere, right? A lot of explosions. And that's the basis of all of our energy. It comes from these particles slamming together and generating a lot of energy. Does anyone have any questions at all? Because I know this is pretty complicated stuff. So, was your hand still raised from before, or?
So,
Oh, you're good. All right. So I'll just recap this one more time, right? The science behind a star is you have hydrogen, right? Hydrogen, hydrogen particles that are slammed together, and those generate a lot of energy. The key thing is that in order for you to be able to slam that hydrogen together, it needs to be very hot. So must be very hot. That's the key point. Must be very hot, must be very dense. The reason for that is because hydrogen, as we know it, is a gas, right? Have you ever taken, let's say, like a water bottle and try to like crush it up when there's still air inside of it, right? That air, well, it can compress a little bit, but you can't compress the whole water bottle down flat, right? Because there's still air in there. Hydrogen is like the same thing. If you had a water bottle filled with hydrogen and you try to compress it, you couldn't compress it all the way down. So that's those hydrogen molecules trying to stay away from each other. They don't want to combine together to form helium because it takes a lot of energy to do that. So inside of a star, it's very hot and very dense. That's the only way this hydrogen is able to fuse. But if that's how hydrogen is able to fuse, where does the hydrogen come from? Right, out there in space, we always know, we're told that there's basically nothing out there, right? There are very few particles, there's suns and stars here and there, but where does the hydrogen come from? The hydrogen comes from what we call a molecular cloud. So the birthplace of a star is, well, obviously in space, but in space, you have these giant clouds of dust and gas, and they're called a molecular cloud. Inside these clouds, you have that hydrogen, you have helium and stuff and that is the fuel for a star. That fuels the fusion. And just like we have, clouds in our sky, which are filled with water vapor, sometimes in space you just have these clouds floating around of just gas, and that's where stars are born. These molecular clouds. And if you think about it, in space, remember, there's no like gravity basically, right? You're free floating in space. So if you imagine a bunch of little particles like this, right? This is your molecular cloud with all this gas and dust everywhere, right? Since you're free floating in space, gravity starts to pull things together, right? No matter how small the object is, even if you had, like if you were in space and you were here, let's say you were here, and there's someone else maybe like a mile away from you, right? Slowly over time, gravity will start to pull you guys together, even though you're so far away. The same thing with these little particles. Since they're free floating in space, gravity starts to pull them together. So maybe this particle comes over here a little bit, like that. This particle gets pulled over here because there's so many more particles here, and it comes over here like that. So the particles start to collapse onto each other. The gravity starts to pull them together. So if you started out with, let's say, 2, 3, 4, 5, 6, 7, 8, like that, those particles, and these particles started to collapse on each other because of gravity, then these particles start to clump up like that. And then as it clumps up, it has more mass. It's a lot heavier. And therefore, as you know, heavy things have a much greater gravity, a much greater gravitational force. And that means that it brings in even more particles from even further away. Particles from over here are now attracted to this big particle, this big clump. And then it keeps on adding onto itself. And we have an even larger clump of gas and dust, right? And since it gets even bigger, it's even denser, has even more molecules onto it, it drags even more stuff around it, into it. So stuff even further away, it's dragged into its core. And as you get more and more dust, as you compact it and take it all and clump it together, that's what we call a protostar. This process of where you take a molecular cloud and its hydrogen and the dust all starts to collapse together, that's where you create a protostar. Is it a black hole? Not yet a black hole. We'll discuss that in a future lesson, but it's a similar process because black holes also use gravity, right? In a black hole, gravity sucks stuff into itself for all around it. And a protostar is governed by the same thing. It also uses gravity to create itself. Because, it clumps stuff together. But a protostar isn't as strong as a black hole. So after we have our protostar, it looks something like this, right? This is an actual image, it's a drawing, but it gets the point across. If you look at all this red over here, right, all this red, that's our molecular cloud, right? That's our gas, that's our dust, that's our hydrogen, a giant cloud of it. And right here in the center, that's our core, right? That clump of molecules that kept on clumping and clumping and clumping, right? Right here you have a lot of molecules and atoms all clumped together really tightly. And it drew in all these other molecules from over here. That's why this part is so black, right? Why do you have this outline here? That's because everything inside that outline was sucked into that core. Everything just sucked into it. And that's what the protostar is, sucking in all this mass, trying to it's getting hotter and hotter and hotter. So what does a protostar mean? Protostar, meaning original primitive, right? Basically means before a star is a star, it's a protostar. That's what it means. And these clumps of molecules and dust, astronomers have a name for it. and we call it a dense core. And what happens is, as I said, the gas collapses towards these cores, and that core gets more and more massive. So let's take a look at this link that showcases. All right, this is a molecular cloud. As you can see, it's a giant, kind of spherical cloud of gas and whatever. And over time, what will happen is you start to see clumps. These dense cores start to form. And at the whiter and the more yellow a section of the cloud is, the more dense it is, the more stuff is there. There, as you can see, right there in the center, you already start to have a pretty dense region where a lot of mass is coming together and clumping together. Right there. Now you see it start to swirl around. And there's another dense core over here. And now the two dense cores have merged together. Here's a third one. And they're all swirling. But they're still gathering more mass, right? Look at this mass being pulled into it, right? All this mass. And here's another dense core that's being sucked into this bigger one. You can see it swirling really, really quickly, right? Right? We used to have that giant cloud of, of gas and dust, and now we see most of that has been compacted into this dense core. That's what a protostar is. So what we noticed in that simulation was, one, there was a lot of spin, right? As you have mass coming together and colliding with each other, eventually what happens is that mass starts to spin in one direction. And you saw that dense core really go really, really quickly, spinning counterclockwise, I think. No, it was clockwise, like this. So that spin in a protostar comes from collisions. Another thing that we noticed about protostars, as you saw it get whiter and whiter and get hotter and hotter and get more and more yellow, that's because you have so much mass. And when you have so much mass and so much gas and dust, and you compact it together, that increases its heat. So one thing to take note of, more dense equals more heat. This is like the most basic law of astronomy. The more dense something is, the more heat it will start to give off. So that's why, as we have more and more mass, our protostar starts to get brighter. You see this section is a lot brighter than the rest of the dust around it. And the last thing is that there are these jets, right? We didn't see it in the simulation, but we see it in the drawing here. We see these jets of matter being shot out into space. Does anyone have any idea why that could be? It's all right. The answer is that the protostar is starting to develop its own magnetic field. So you know how our own star has a magnetic field. This is the protostar phase, is when its magnetic field starts to get born. And as we saw in the simulation, we saw dense cores being brought over from all over the place, and there's a lot of swirling, a lot of collisions everywhere, and it's really chaotic, right? And so when it's so chaotic, its magnetic field is also really chaotic. And as a result of that, we have these jets of matter. After a bit matter gets sucked in, sometimes it gets caught in a really strong magnetic field, and then it gets shot out into space. It's over here. gets caught in a really strong magnetic field and boom, gets shot out. So those bits, those jets are because of its developing magnetic field. Let's recap what a protostar is again. Protostar is after you have a dense core that gets compacted together, starts to suck in all the dust around it. It becomes hotter, right? Hotter, it starts to spin, it starts to release these magnetic jets. After the protostar phase, it becomes what we call a main sequence star, right? What I mean by it transitions at 10 million Celsius is that after you keep compacting dust and dust, you get hotter and hotter and more dense and more dense. At some point, you have so much mass that it becomes so hot that it reaches 10 million Celsius. I can't even think about how hot that is, but it's really, really, really hot, right? And once it reaches that temperature, that is what it is hot enough to start fusing hydrogen, right? 10 million Celsius is what a star needs to get to start fusing hydrogen. That's so hot and so dense that those hydrogen molecules inside the star start to come together and start fusing, right? That's really, really hot, really, really, really dense. And for a protostar to become, right, for a protostar that looks kind of like this, with this disk around it, right? That's what a protostar looks like. To become a main sequence star and become that hot, it sometimes takes from 1 million to 10 million years. It takes a really long time to become a main sequence star. But after it does become a main sequence star, it's basically absorbed all the dust and gas that it can around it. There's no more collisions from anywhere else in space because you already sucked all of it into yourself. There's nothing else around you. And therefore the star starts to calm down. It's not going to have the magnetic jets anymore because it doesn't have so many collisions. There's no more mass entering it. This is, however big the star is going to be, it's not going to change basically at all because there's no more collisions. There's no more chaos. So a main sequence star, after it collects all the mass that it can, doesn't change much and it kind of looks like that. Our sun is a main sequence star. And it hasn't changed much at all in the past 10 million years. And it will continue to stay like that, just in the sky, fusing hydrogen inside of its core until all of its hydrogen runs out. And how long that takes could be for anywhere from 10 billion to 100 billion years. So our sun still has about 10 billion years left in its lifespan. So it's going to be here for a long, long time, much longer time than we're going to be around for. But that's a main sequence star. It calms down and it starts to just fuses hydrogen nice and calmly. But sometimes a star doesn't have enough mass, right? Or if we had a protostar, right? Let's say we had a really big dense cloud, right, like this, and then a protostar formed right here in the center, right? Then it becomes a main sequence star, right? But sometimes, let's say you had a really, really small cloud, like this is a really small cloud of dust, and it still formed a protostar, but that protostar is a lot smaller than the other one. And if there's not enough mass, then it's not going to be able to fuse hydrogen. Because if there's not enough mass, it's not dense enough. And if it's not dense enough, it's not hot enough. So if a molecular cloud has what we call 8 or 0.08 solar masses or less. So what is a solar mass? A solar mass is how heavy the sun is, basically. And the sun is a 2 with 30 zeros after it. You get the picture. And this is kilograms. So a 2 with 30 zeros after it, number kilograms. That's how heavy the sun is. So it's really, really, really heavy, right? But sometimes there's not enough mass for it to create a star like the sun. Yes, Rena?
How do people measure the weight of the sun?
How do we figure out the weight of the sun?
Yeah.
I mean, maybe they just.
Well, that's another question we're going to be studying in detail in another lesson, but to give you a sneak peek, basically, we look at the light from the sun. We look at the light and basically determine what wavelengths, how strong that light is, and it tells us a lot about the sun. So we'll give you a more detailed answer later. But sometimes, going back to our slide, sometimes there's not enough mass, right? If you have a really, really small cloud like this, we don't have this much mass inside of it. You have something a lot less than that. And if there isn't enough mass, as I said before, it's not dense enough, not hot enough to fuse hydrogen, unable to fuse hydrogen. So after it's collected all the dust that it can from its molecular cloud, it gets hot. It does get hot because, of course, it's still pretty dense, a lot denser than our own Earth, a lot bigger than our own Earth, right? But just not hot enough to fuse hydrogen. So instead, what a brown dwarf is just a cooling ball of gas. That's what we call a brown dwarf. Not big enough to fuse hydrogen. It's a brown dwarf. So here is what we look at the structure, the brown dwarf. As you can see, these are just clouds of hydrogen kind of swirling around. And there's some storms and stripes, right? Storms all over. And a question that's plagued astronomers for many years is, what's the difference between a brown dwarf and Jupiter, right? If you look at Jupiter, well, Jupiter kind of looks like this, right? Let's pull up a picture of Jupiter. We'll compare. All right. You see these clouds of swirling dust and storms all over? It doesn't look too different from what we see here, right? And some astronomers believe that Jupiter is a brown dwarf. It was pretty massive, right? Really, really massive, but just wasn't massive enough to start fusing hydrogen. So you can think about that Jupiter is a brown dwarf in our very own solar system. That's pretty cool. But if you look at these pictures here, this is showing the cooling process. So you start out as a really, really bright, a really orange ball of hydrogen and gas, right? But it's not hot enough to fuse hydrogen, so it can't create its own light. So over time, space is really, really, really cold. So it starts to cool down that ball of gas and becomes a bit redder. And then it loses a bit more color and becoming a bit more like a magenta, becoming a bit bluer. And eventually it becomes basically just a black ball of dust, not emitting any light, and it's kind of just invisible to us. Those are brown dwarfs. That's what we call a substellar object. Substellar meaning like below, and stellar meaning star. So below star, right? Not exactly a star yet. Those are brown dwarfs. So let's recap a bit. What is a star? Right? We learned that a star has to be hot enough to fuse hydrogen. It needs to be hot enough to fuse hydrogen. Why are they so bright? Fusion, right? When you have hydrogen atoms coming together and releasing a lot of energy, most of that energy is released as light. And that light makes its way out of the star and into our eyes and creating sunny days and powering our solar energy. Where do stars come from? Molecular clouds. Molecular clouds. Giant clouds of gas and dust floating in space that compact together to create a protostar. So let's draw it out. We have molecular cloud that turns into protostar. These are our jets. After it takes all the mass that it can, there's no more mass around it, it calms down and becomes the main sequence star. And now it starts fusing hydrogen, and it continues on for 100 billion years or so. Sometimes, if that cloud is really, really small and there isn't enough mass inside of it, not enough to fuse hydrogen, then it becomes a brown dwarf. And as a brown dwarf, it will sit there and just cool off for the rest of its life. So that's where we are so far. Molecular cloud, protostar, main sequence, or a brown dwarf. Any questions? All right, I'll continue on. So next, we're going to introduce what we call the Hertzsprung-Russell diagram. This is probably the most important diagram for astronomers because this is how we classify stars. So this looks like a really complicated graph with lines everywhere and a bunch of dots and a bunch of scales and everything, but I'm going to break it down really simple. The first thing we need to talk about to understand this graph is called luminosity. So luminosity is measuring how bright a star is compared to the sun. So if you look over here, what it says is luminosity, sun equals 1. So let's say you had our sun, right? This is our sun. Let's say how bright it is, we give it a number. We say it is brightness 1. If we had a much bigger star here, like this is massive, right? It's a big star. It's probably a lot brighter than our own sun, right? It's fusing a lot more hydrogen and whatever, and therefore it's much brighter. So let's say it has a brightness of 100, right? As 100 suns worth of brightness. And let's say we had a star that's even smaller, like this. Here's a star that's smaller than our sun. And it's not as bright as our sun. So let's say maybe it has 0.1 solar brightness, kind of, right? So luminosity is all based around our sun. How many suns is it bright, basically? So that's what the luminosity is showing, how bright a star is. So as we move up the scale, we see these stars over here are much brighter, right? Almost 100,000 times as bright as our own sun. But stars over here are like much, much less bright compared to our sun, right? 0.01 luminosity. So that's luminosity. The next measure of brightness is what we call absolute magnitude. So the issue with luminosity is that it's based around our own sun, right? It's compared to our own sun. That's how we measure other stars, right? But let's say we were an alien planet, right? An alien planet is a very distant, galaxy far, far away, right? If they were to look at this chart and they wanted to know how bright a star was, and we only had luminosity, they wouldn't know how to read that because they don't know what our sun is. They don't know what our star looks like. So what the scientists wanted to create was what we call an absolute or an objective way of looking at stars and how bright something is without having to rely on our own sun. So how they decided to do that was that they wanted to look at a star. So this is our star. They wanted to look at it from 10 parsecs away. This was you, right? You were looking at it from 10 parsecs away. So what is a parsec, right? Well, 1 parsec is 1 parsec is equal to 3.2 4.26 light years. Does anyone know what a light year is?
A very long distance.
That's true. It certainly is a really, really long distance. So, but exactly how long is it? Right, let's explore that. All right, so we know that light travels really, really quickly, right? It goes super fast, right? Super, super fast. Exactly how fast? 300 million meters per second. That's how fast it is. 300 million meters. This is the fastest you can possibly go in our universe, the fastest possible thing in our universe. So light is going incredibly fast. But the thing is that it's not going infinitely fast, right? It doesn't go from one place to another point instantly. It takes time, right? A very short amount of time, but still takes time. Now imagine if this light traveled, let's say from point A to point B over here, right? And this light particle is just traveling, zipping off. And this distance was so far that it takes light a whole year to travel, right? That's how far this is. Between A and B, it takes light a whole year to get to. And that distance is what we call a light year. So it's a really, really, really far, really, really, really far. And if you took 10 of those, basically, or 32 of those light years, that's what you get, 10 parsecs. So if you look at it from a really, really, really far away distance, it takes light 32.6 years to reach that distance. That's how far away you're looking at this star from. But the thing is that since we use absolute magnitude to describe, how bright that star is, anyone, even aliens really, really far away, can also use absolute magnitude, right? They can look at a star from 10 parsecs away, and they will also get the exact same measurement as us. So they can agree on how bright a star is. That's what we call it absolute, right? Everyone can use the same measurement and come to the same answer. So that's luminosity and magnitude, just basically telling us how bright a star is. And the same thing with that. The higher and higher you go on this graph, these stars are a lot brighter than these stars down here, right? Because look, the luminosity is a lot smaller and their absolute magnitude is a lot smaller. All right, the next is we have color, right? Color is pretty simple. It even says right here, blue versus violet, basically. The more blue a star is, as you can see here, the more blue it is. It's that simple. That's what color is, right? The more blue something is, the more blue it is. Then as you add more yellow to it, it becomes a bit whiter. Add even more yellow, it gets this faint yellow color. Add even more yellow, you have a really, really deep shade of yellow. Add even more, you have a bit more red now. You add a bit more red, you get some orange stars. And then once you lose all of the blue, you have no more blue, you have only red. And you just have like this magenta, violet type color, right? So that's all that color is, just what color a star is. And scientists classify the different colors into these groups. So the first group we have is the O class stars. These stars are incredibly blue, right? If you look at, that's pretty blue. These are pretty blue, right? Those are O-type stars. B-type stars, they're still blue, but they're a bit more faint, a bit more white, right? Not as a strong blue color. So those are B-type stars. A-type stars, these are like your pure white stars. F-type, kind of a bit yellow, right? G-type stars, a very deep, strong shade of yellow. K-type stars are your oranges, and M and below, those are your reds, right? So all this spectral class is putting the color of a star into basically like a bucket, right? All your O types are blue, B, a little bit faint blue, M stars, really deep red, G stars, yellow. Our very own star, our very own sun, is right here. Sun, right there, right? Luminosity of 1, right? That makes sense because our sun is, just as bright as our own sun. So here's another look at that same graph, the same HR diagram. You can see here, now we've labeled our main sequence stars, right? Our main sequence stars run along this track here. So we're worried about all this stuff later, so don't worry about that right now. Right now, I just want us to focus on the main sequence stars. So the reason I bring this up is that depending on how big that molecular cloud is, you're going to get a really, really small or really, really big main sequence star, right? Let's look at this O-type star here. Right? This O-type star is absolutely massive, right? This guy had a really massive molecular cloud that created it. And as a result, it's going to be really bright, really dense, and really blue. So that's why it's all the way up here, right? This is where we have our O-type stars. It's going to be really bright, and it's going to be really blue. That's what this region is showing. Let's take a look at our M-type star here, right? At M-type, well, its molecular cloud was a lot smaller, right? It's a lot more red and doesn't have as much mass. It isn't as hot. So that's why that M-type star is basically about here, right? As you can see, more red, and it's a lot less bright than our own sun. Our sun is a G-type star. To be specific, G2. It's a G2 type star. And we are right here, basically. That's where our sun is. So depending on how big the star is, it'll be more bright or more blue or more red, right? I just wanted to showcase, and I really like this image a lot because it shows how all the different colors of stars show you how dense it is. So I know Serena brought up a really good question before, asking how do we know how big our sun is? How do we know how massive it is? Well, we can look at its color, right? A color tells us a lot about how big the sun, a star is. So since our sun is a much more yellowish type color, that's why we know it's about 2 with 30 zeros after it kilograms. Yeah. All right. So now we learned a lot about how big stars can get, right, with main sequence stars. But now we're going to look a bit more inside the star. What about the structure of a main sequence star? What makes it create energy? Why does it look so bright? And stuff like that. And what about these things about solar flares and prominences that you sometimes hear about, or a solar storm, right? How does that happen? And that's what we're going to dive into. We're going to start at the core, and we're going to make our way out, learning about the radiative zones and convection zones, learning about the atmosphere of the sun, its photosphere, chromosphere, and then coronas, flares, and prominences. All right, so let's start. Here we have our core, right? The core is the hottest part of a star. It's made out of really hot, dense plasma, right? So what is plasma? Does anyone know? Plasma is actually a fourth state of matter, right? So we know we have solids, we have liquids, we have gases, and we have plasma. Plasma is basically, well, it's kind of like a gas, but imagine it's a super, super, super hot gas. It's so hot that the atoms start to split apart. They start to split themselves apart. That's how hot it is. So it's incredibly hot. As we said before, it's at least 10 million degrees Celsius. So very, very, very hot. That's why all that gas has become plasma. And since you have so much mass there, so much gas all compacted, gravity, squeezing everything together. It's incredibly dense, right? Hot, dense. The two always go hand in hand. And that's where our fusion happens. Inside this core, we have hydrogen atoms coming together, explosion, forming helium. Over here, same thing is happening, bang, helium, right? So these reactions are happening all over the place inside the core. Explosion, 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 explosions everywhere. That's all happening inside the core all the time. And this is why the main sequence star doesn't change its shape a lot. It is what scientists call a self-correcting hydrostatic equilibrium. So let's explain the process first. First, let's look at our core, right? Our core looks like this. Inside our core, we have a lot of fusion, and fusion creates a lot of energy that wants to get out of the core. So it pushes the core out. It's a lot of explosive energy, these explosions and bangs happening all the time. So boom, the core gets a lot of pressure, and the core gets a bit bigger. Right, so that's that. The core heats up and expands, gets bigger. But since it gets bigger, its density is reduced, right? The core is still the same mass, but now you increased how big the core is, and that means it's less dense. If it's less dense, that means it's not as hot. And if it's not as hot, you don't have as much fusion. So therefore, you have a much smaller force pushing out. And if you have a much smaller force pushing out, then gravity starts to take over again. It tries to compact the core down. So therefore, the core gets smaller again. So the core contracts, and therefore, the cycle restarts. If the core gets smaller, the rate of fusion gets higher because it's more dense, gets more hot, and therefore the core heats up, expands, and then just keeps on going. It expands, contracts, expands, contracts, expands, contracts. And that's what we mean by it's self-correcting, right? If it gets any bigger, then it has to collapse back down. If it gets any smaller, it has to expand back up. That's what we mean by self-correcting. The second part is we call hydrostatic. What hydrostatic means is basically under pressure, right? Inside the core, there's a lot of mass all compacted together, so it's really hot, there's a lot of pressure. That's what hydrostatic means. And equilibrium means the same. It's staying in the same state, right? And since the core can't expand or contract any more than it is, then that's what we mean by equilibrium, staying the same. So that's what's happening inside the core. The next part is what we have is the radiative zone. So right outside the core, it's still pretty hot, but it's not 10 million degrees Celsius. It's not that hot. So this is just where a bunch of hydrogen is living, a bunch of particles here and here and here, but it's really, really, really dense. Right? It's super dense. And so after light and these explosions happen in the core, it starts to make its way out. And it starts bumping into all these particles, right? Boom, 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 trying to escape the core. That's basically what the light is trying to do. That's the radiative zone. Boom. That's what's happening in the radiative zone. This radiative zone is so dense that light only travels a short distance before colliding with another particle, right? So if you can imagine, like if you were a light particle, like if there's all these different particles inside the radiative zone, right? If you were light, you bump into this one, bump, 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 and your light gets kind of basically trapped inside the sun. So that's why it takes almost 171,000 years to go from the core, from here, to leave the radiative zone. Because it's so dense, and that's why it takes light so long. And so in the core, which is incredibly hot, our sun is roughly about 15 million degrees Celsius at its core. At this point of the core, it drops to 1.5 million C. So there's a huge drop off in the temperature. So it becomes a lot colder. The next part is what we have is the convection zone. That's right outside the radiative zone. And this zone is probably the coolest part or the most interesting part about the sun. Let's take a look at this.
マジック・ザ・ギャザリング待望のモバイル版の登場で毎日がかなり充実している
So what this video is showcasing is introducing you to the concept of convection. So let's describe what's happening in this video. On the right here, we have a hot table underneath. Or we have a hot table right here. And this is a bunch of smoke vapor. And as that smoke vapor touches the hot table, as we know, hot things rise. It starts to rise up. And as it rises up, it gets away from the hot table. So it no longer can heat itself. It starts to cool down. And as we know, cold things fall. So therefore, it rises from the hot table, cools off, falls, comes back down to the hot table, gets heated up again, goes back up, cools down, falls, heats up, cools down, heats up, cools down, and starts swirling. It creates convection. Convection is just this circle of cooling and heating and cooling and heating over and over. This same process that's happening inside this glass and with smoke vapor also happens within our very own sun. Basically, all that heat, all that light and hydrogen and gas, it flows like this inside the sun. It flows. It gets heated up. It comes to the surface of the sun. It gets much colder and drops right back down. Comes up, cools down, drops back down, heats up again, and keeps on going, these loops. And these convection currents form what we call convection cells. These are what these cells are. These walls, these darker lines, that's because they're darker because that's colder, right? If you look, it cools off right here and starts and falls back down. That's why you see these dark lines. That's because those are the parts of the gas that are cooling down and falling back into the sun. So if you look at it right here, that's our radiative zone, right? It gets trapped all over the place, bump, 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 and then it hits our convection zone. And then starts convecting, 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 forming these cells, convecting, right? That's a convection zone, where all this mass and gas all just convecting like that, carrying heat from the radiative zone out into space. So that's how light goes from our radiative zone after traveling for 170 million years or 1,000 years, then follows a convection current and gets released into space. So that's how that works. So that's what the convection zone does. Let's skip this. All right. So after the convection zone, we hit the sun's atmosphere. The first part of the sun's atmosphere, as we call the photosphere. This is the part of the sun that is directly after the convection zone. So this is the very top of the convection zone. It's the same image as we saw before, right? Look at these convection cells. There's a convection cell right here. There's a cell right here. And as you can see, the centers of these cells are really, really hot. This is where the hot gas is coming up. And then it cools down to the sides. Cools down, and it falls back down inside these darker lines. And this is showing you what the convection of the sun looks like. These convection cells going like that. So that's what the photosphere is. And each one of these convection cells, the sun is always changing. It's like like have you ever cooked at all or boiled water, right? You see bubbles popping up here and there. And it's always changing because it's always super hot, right? The same thing with the photosphere. It's always changing. All these cells are being created and then they disappear. And each one of these convection cells only lasts about 20 minutes before they get kind of like swarmed or they just disappear entirely. Another important thing is that besides carrying gas, these convection cells also carry the sun's magnetic field. if you can imagine an arrow pointing out, like an arrow pointing out of each one of these convection cells straight at you, right? Straight out of your screen. See, there's another arrow here, right? Pointing at you here, another arrow here. And that's the magnetic field of the sun. It's being carried out by a convection cell and then released into space. That's what the photosphere does. The next part we're looking at is the chromosphere. Actually, no, before that, let's look at a couple images of the photosphere. I wanted to demonstrate for you how it's always moving. Look at that. Right, you see how it's like kind of like boiling and things are rising and falling all the time. Here's another close-up on this website's page. Look at it, right? Each cell is kind of shifting around and it's boiling and the heat going up and falling and convecting all over the place. That's what the surface of the sun looks like. That's what the photosphere is. All right, I think that's pretty cool. All right, but moving on, next is the chromosphere. The chromosphere is made out of what we call spicules. If we zoom in on this picture, you see how it kind of looks like hair all over the place, like that. There's a hair there, hairs and hairs like that. Those are what we call spicules. And these spicules are basically like grass. They follow the movement of the sun, of the sun's magnetic field. And this layer sits right on top of the photosphere. Do you remember all those arrows that we were drawing before? These magnetic field lines? On top of every single one of these convection cells is a spicule. And that follows where the convection cell's magnetic field is going. So if it all sways in one direction, the spicules sway in one direction. If it sway in another direction. So you can think about the chromosphere as basically grass, right? Grass swaying in the wind. But on the sun, that grass is on fire. So each one of these spicules are also very short-lived, right? They only last about 10 minutes before they disappear. All right, I'm probably gonna go over maybe about 10 minutes or so. So if you guys want to, so class technically now is over, but if you would like to stick around, feel free to. I'm gonna continue on for about 10 minutes and we're just only have a couple of slides left, all right? So after our photosphere, we have our corona. So right here is what we have when we had an eclipse, right? This black stuff right here is actually the moon. The moon blocked the sun, and as a result, we're able to see this last final layer of the sun called the corona. And inside the corona is where all the cool stuff happens. This is all stuff inside the corona. Right here is where we have a solar flare. You can see this is actually the sun itself, mass from the sun being thrown out into the corona. Here we have a prominence, a filament of the sun following as a magnetic field line. So this is all hydrogen and stuff following the magnetic field of the sun, all right? Being thrown out into the corona. Same thing here. You can see how the mass of the sun is just following and flowing with the magnetic field lines. And same thing here. Here's another zoomed in picture, right? You can see all this mass crisscrossing and the magnetic field going one way or the other. And over here, right? The magnetic field of the sun is very chaotic. It's going all over the place. You can see in all these images, right? Here, here, here. And that's what creates these really cool events. Solar prominences, solar flares, and coronal mass ejections. So what's a solar flare? A solar flare is basically a sudden flash of light on the sun. What happens is the magnetic field of the sun kind of collapses on itself. It converges with itself. It like battles with itself kind of. And when it connects together, we get a solar flare. Let's open this. So watch this. Boom, like that. Let's watch that one more time. That's your solar flare. And next, we have what we call a prominence. A prominence is what happens when you have these filaments, those spicules inside our chromosphere. If they ever connect with each other, same thing, like it's all because our sun has a really chaotic magnetic field, then it forms what we call a prominence. So let's look at this. Boom, a prominence appears. Watch that again. In slow motion. So a bit of the sun just erupting away from itself. And so these prominences, even though that appeared really quickly on the Wikipedia page, they actually last for a really, really long time. As it expands and comes up, that might take anywhere from a day to a couple months to appear. The last important thing about the sun is that they're what we call coronal mass ejections. So remember that solar flare that we saw and that prominence that we saw? Those are bits of the sun being ejected out into space. And that's what we call a coronal mass ejection, release of the solar plasma, the solar gas being released into space. So last bit, why do we care about the structure of the stars? Yes, we're gonna go ahead.
Maybe they might explode on us or something. Or we need to know more about outer space, I guess.
Yeah, sometimes stars can explode, right? Or we just need to learn more.
And also, we want to know if there's life on other planets. So if a sun is like the equal distance, a star is the equal distance from a sun to Earth, there might be life on the planet because it's probably not too hot.
Yeah, there might be life on other planets, and depending on the star that that life is surrounding on, that might change, right? So yeah, these are all really good answers. They could explode. That pose a danger for our own life, right? We can learn more about space. We learn more and we get some pretty cool knowledge, and we can also learn about other life on other planets. Yeah, definitely. I had some answers of my own, and I said, well, we care about the stars because it gives off heat, it gives off life, right? It gives us all this sunlight that we use in our everyday lives, right? Outside my window right now, I see sunlight everywhere, and everyone's wearing short sleeves because it's not, in space it's super cold, but because we have the sun, we're not dying of coldness, right? For humans, for us, it helps us create vitamin D, right? That's a very important vitamin to make sure that we stay healthy and our skin and our muscles don't deteriorate, right? Also, in the past decade, we've had a huge increase in renewable energy, right? We have solar panels and stuff like that. It helps us, generate more energy and move away from fossil fuels and make sure we don't have climate change, and also helps us prevent disasters. So for example, let's look at this. All right, open link. Yes. So watch this video here. This is one of those coronal mass ejections. Watch this right here, right there. You see that massive, watch it again. These waves of the solar mass being ejected into space. This one happened back in 2012. And luckily, Earth is actually right here. Our very own Earth is right here. And if you see this giant storm is about to appear, boom, it just misses the Earth. And it's really important for us to know about when the sun's gonna like explode on us and release and have a coronal mass ejection. Because if we don't know and don't know that much about the sun,
Higher density plasma,
this is what
a
might happen
stronger
to us.
magnetic field carried within the CME, strikes Earth's field and significantly
So this is what
alters
happens when
the
a
structure.
coronal mass ejection
Here we see the
hits
dramatic
on
changes
the Earth.
in Earth's magnetic field
All these lines
and the
that
shape
you
of
see
the
here
magnetopause
are
as the
the
CME
magnetic
passes
field
Earth.
of the Earth.
But close to Earth, the magnetic field is largely unchanged. Earth is protected from the intense solar event. This is the case for a rather ordinary CME. In this example, a CME launched by an X3 flare from December
a really small
2006.
storm kind of hit us.
But what would happen in the
and
case
it
of a
kind of
more
bent our
intense
magnetic
event,
field back a little
such
bit.
as the Carrington
But this is what
event
happened in
1959? With the aid of
Look at
similar
how strong
computer
that solar
models as
wind is.
before,
Right?
we
All
can
that solar
explore
mass
some of these
hitting our magnetic
possibilities.
field and
Here,
completely
a much
destroyed
stronger
it.
CME
Look at that, right?
compresses
Look at all that
the
red.
magnetic field
We have no
between the sun and
protection
Earth
at all
and generates
from
more density in the
the
bow
solar
shock,
wind and the solar
represented
mass.
by darker red.
And why this is really important to us is because we are really dependent on electricity, right? Your lights are being powered, your Wi-Fi, your phones, everything in our lives these days is basically controlled by electricity. And the sun's mass is basically, it's an electricity killer, basically. It kills all of our electronics. So if that solar storm were to ever hit us, then we would basically have to restart all of our technology. Overnight, our microwaves and phones and hospitals would all instantly break down. And so that's why it's really important to learn about the sun. Otherwise, our magnetic field would get destroyed just like this. So it's really important for preventing disasters. And now the very last thing I wanted us to look at was just this one link. I think it was a really nice kind of like recap to our lesson. Where is it? Hello? Here we go.
Spectrum Business can help you cut costs by cutting your internet and phone bill in half.
Great, but I doubt.
The city sky is frankly rather boring. If you look up at the patches of murk between buildings, you might be able to pick out the Big Dipper, or perhaps Orion's Belt. But hold on, look at that murky patch again, and hold out your thumb. How many stars do you think are behind it? 10? 20? Guess again. If you looked at that thumbnail-sized patch of sky with the Hubble Space Telescope, instead of points of light, you'd see smudges. These aren't stars. They're galaxies, just like our Milky Way, cities of billions of stars, and more than 1,000 of them are hidden behind your thumb. The universe is bigger than you can see from the city, and even bigger than the starry sky you can see from the countryside. This is the universe as astrophysicists see it, with more stars than all the grains of sand on Earth. By staring up at the stars at night, you've taken part in the oldest science in human history. The study of the heavens is older than navigation, agriculture, perhaps even language itself. Yet unlike other sciences, astronomy is purely observational. We cannot control the parameters of our experiments from lab benches. Our best technology can send man to the moon and probes to the edge of the solar system. But these distances are vanishingly small compared to the yawning gulfs between stars. So how can we know so much about other galaxies, what they're made of, how many there are, or that they're even there at all? Well, we can start with the first thing we see when we look up at night, the stars. What we are trying to learn is their properties. What are they made of? How hot are they? How massive? How old? How far are they from Earth? And believe it or not, we can learn all of these things simply from the light shining in the sky. We can decipher one kind of stellar message by turning starlight into rainbows. When you look at a rainbow on Earth, you're really looking at light from our sun being scattered through water droplets in the atmosphere into all the different wavelengths that make it up. And when we study the light from other stars, we can create rainbows on demand using not water droplets, but other specific instruments that disperse light. When we look at the scattered light from our sun, we see something strange: dark lines in our rainbow. These lines are the characteristic fingerprints of atoms. Each type of atom in the solar atmosphere soaks up light at specific wavelengths, and the amount of absorption depends on how many of these atoms there are. So by observing how much light is missing at these characteristic wavelengths, we can tell not only what elements are in the sun's atmosphere, but even their concentrations. And the same idea can be applied to study other stars. Make a spectral rainbow, see what's missing, and figure out which elements are present. Bingo! Now you know what stars are made of. But we aren't restricted to just the wavelengths that our eyes perceive. Consider radio waves. Yes, they can bring the Billboard Top 100 to your car, but they can also travel almost unimpeded through space. Because they've come so far, radio waves can tell us the very early history of the universe, from just a few thousand years after the Big Bang. We can also study the infrared light emitted by colder objects like the gas and dust clouds in space, and the ultraviolet light from the hot stars recently born from those clouds. Studying different wavelengths not only gives us a more complete picture of any single object, but also different views of the universe. For this reason, astrophysicists use several different kinds of telescopes, covering the spectrum from the infrared to the ultraviolet to the X-ray, from giant radio dishes to giant silver mirrors to space satellites detecting light that would be otherwise blocked by the Earth's atmosphere. Astrophysicists don't just see the billions of stars among the billions of galaxies in the universe. They hear, feel, and sense them through many channels, each revealing a different story. But it all begins with light, the kind we can see and the kind we can't. Want to know the secrets of the universe? Just follow the light.
So I thought that was a really cool little way to wrap up, like at least or summarize, give like an overview of what we'd like to study in astronomy, right? And to answer your question, Serena, or like how do we know how big the sun is, like how heavy it is, or what it's even made of, right? As the video said, we look at the light, right? And it went into detail about looking at the spectrum of light and the different wavelengths and how different atoms have different like absorption and stuff like that. Well, we'll learn about that as well in a different lesson as how do we study stars. But I think it was really cool how you talked about basically how broad astronomy is, right? Covering things from our very own sun to other stars and other gas clouds, and even learning about the beginnings of our own universe with the Big Bang, right? That's really what astronomy all is: looking at something and finding theories on how it came to be. All right. So a short sneak peek at our next class's lesson. We're going to be covering basically everything on this chart, but let's look at where we started. Today we learned about molecular clouds, right? That's where stars are formed. Then we create protostars, right, inside those molecular clouds. And from there, we can get our different types of stars, right? We have our main sequence stars. So if it doesn't have enough mass to fuse, it becomes a brown dwarf. If it has a lot of mass, it becomes low mass star, or it has even more mass, it becomes a massive star. So we've really only reached this portion of our graph, right? In future classes, we're going to dive into supergiants and giants and look at nebulas and supernovas, black holes and neutron stars and stuff like that, right? So that's a little sneak peek at what we're going to be studying in the future. Does anyone have any final thoughts on anything before I end class?
Not really.
All right, cool. Well, I hope you guys enjoyed our first lesson. I know I went into a lot of detail and probably rambled a lot, but I hope you found at least some of it really interesting. I hope to see you next class.
Thank you.
All right, see you.
Bye.